All right, so now we know that the carbon-based life is common in the universe, at least on Earth, because we know that life exists only on Earth by now at this point. So we know that the carbon-based life is common on Earth. So there are requirements for carbon cycle in order to maintain this requirement for life, right? So those are liquid water, carbon, and the energy source of life. So let's look at each of these in step by step. So the liquid water, so you know water is H2O, so we need to have two hydrogen atom and oxygen in one water molecule. So here in this diagram you may see a picture of a hydrogen atom where we have one proton at the nucleus and one electron which is orbiting around the proton, and on oxygen atom we have you may count the number of electrons. So here we have two electrons in the inner shell, and then we have 2, 4, 6 in the outer shell. So we have altogether we have 8 electrons that orbit around the nucleus, and in the nucleus we can find 8 protons. So here, as you see, these electrons are stay there as a couple, but here these 2 electrons need more 2 extra electrons to make it neutralize. So it's easy to make a bond between hydrogen and oxygen because oxygen is in need of an electron, and hydrogen is always willing to share this electron or catch another electron to the atom and make it neutral, right? So here a molecule of water consists of 2 hydrogen atoms attached to an oxygen atom. In water, each hydrogen atom donates its electron to the oxygen, and it's left as little more than naked proton hanging on outside, right? So here in this picture, you may see it a little bit carefully. So we are basically not just giving the electron from hydrogen and leave it there, but really it's just living together like this. So these 2 electrons are sharing among the oxygen and the hydrogen. And same thing here. So 2 electrons being shared between hydrogen and oxygen. Here on the oxygen atom, we see a net negative charge, and on hydrogen, we will be seeing a net positive charge on these sides, which make it easy to make bond with as a chain with other hydrogen molecules and oxygen molecules. So these bonds are called the covalent bonds or the hydrogen bonds. So these are the bond between the oxygen and hydrogen. Basically here, this bond is a covalent bond, and this one is a hydrogen bond. So hydrogen bonds are stronger than the covalent bonds. Then the liquid water. So the molecule of water consists of 2 hydrogen atoms attached to an oxygen atom, as you know. So in water, each hydrogen atom donates its electron to the oxygen, and it's left as little more than a naked proton hanging on outside, right? So that's what we learned earlier. So the oxygen then has a negative electric charge, like in this one, as I mentioned. So it has have a net negative electric charge, while each of the hydrogen has a positive electric charge. So the special properties of water come from the non-symmetric way that the 2 hydrogen atoms are arranged. So here it is a little bit like triangle shape, right? So it is not really arranged symmetrically. Then because opposite electric charges attract, there's another attraction between the positive charge hydrogen atom and any negative charge. So here it can attach to this hydrogen on a one single water molecule can attach to another oxygen. As I mentioned earlier, it gives the possibility to create this chain of water molecules. So similarly, there's another attraction between the negative charge oxygen atom and any positive charge atom. So here closely there's a hydrogen which is negatively charged, so they will bond together and create a hydrogen bond. So the hydrogen bonds between water molecules serve to keep water liquid over a very large range of temperatures. So as I mentioned, hydrogen bonds are stable. So this bond keep the possibility of water to stay in liquid form phase for a range of temperatures. So best example is thinking of a group of square dancers who are in constant motion but are always holding the hands of other dancers. So water is just like that. So they're dancing around, but they're not leaving the hands. They will be holding the hands together. So at low temperature, the molecules slow down until the hydrogen bonds form a very open crystal with each molecule bonded to just 4 neighbors. So it's create ice crystals when you lower down the temperature of water, right? So this hydrogen bond will be still holding hands but freezes out. So the you may think about, like, if you put a water bottle, like a glass water bottle, into the freezer, most of the time the glass bottle will crack, right? So that's due to the water freezes from up to bottom, right? So the ice crystals that takes up more space than the square dancing molecules of water in liquid form. So water expands when it freezes. So when you have that water bottle, the top part of the bottle will get frozen and it's less dense. So it will expand. So that's why the water bottle get cracked. So anyway, so without that very special property, lakes and ocean would not freeze from the bottom up and would mostly stay frozen all year. So the less dense ice floats on top of water, as in this picture, and provide the isolation that keeps the rest of the freezing and protects any life forms below. So usually, you know, like we are doing ice fishing. So that's because we can find water in the lakes below this frozen ice crystal layer. So besides its ability to stay liquid and to freeze in a friendly fashion, water forms hydrogen bonds with many different kinds of molecules. So thus holding them in solution, and in many cases bringing different molecules together so that they can react. So all of this process of life take place in this sort of water solution environment. And it is very important for the life to be carry on. So here on Earth, carbon is incorporated into living things as carbon dioxide. So we feel like carbon dioxide is a greenhouse gas and we don't need it, right? That's what we feel. But carbon dioxide does a very good job in the Earth. However, having more than enough carbon dioxide create the problems. Anyway, so because it is a gas that dissolves in liquid water, it is a particularly convenient and portable source of carbon. You know, it is carbon dioxide, right? So it is carbon dioxide is a good source of carbon. So other source of carbons are meteorites, so contain complex organic compounds, example amino acids and other complex hydrocarbons. So arguments about whether or not these particular hydrocarbons came from space or are the result of earthly contamination have not yet been settled. So hydrocarbons do exist in space, since we see their spectral signature in the radio waves from interstellar clouds. So example, the signature of a simple sugar, glycoaldehyde, was found recently. So glycoaldehyde is this structure where we see 2 carbon bonds, then 2 carbon atoms bond together, and 2 hydrogen over here and the hydrogen here, and a double bond between oxygen and another oxygen with another hydrogen atom. So this glycoaldehyde, which is a simple sugar structure, was found recently by the radio wave, by the spectrums. So the early Earth may have had an abundance of such hydrocarbons to jumpstart life and the carbon cycle. So other possible sources of carbon, particularly methane, could provide alternative to carbon dioxide as the portable form of carbon. So Titan, for example, is known to have large amount of methane in its atmosphere. So you know Titan is, right? So Titan is the largest moon that you can find in the solar system. So the carbon return process. So in order to complete the carbon cycle, there must be some way to return all of the carbon to its portable form. So here on Earth, the carbon tend to end up in a sediment on the ocean floor and combine with calcium in surface rocks. So the return process here is a plate tectonics, which recycled the surface into the hot interior of the planet and returns carbon dioxide to the atmosphere through volcanic actions. So plate tectonics require a planet that remains semi-molten except for a thin surface crust. So, you know, like on Earth, the plate tectonics are active and they keep moving around. So here, plate tectonics requires a planet that remains semi-molten. So Earth is semi-molten crust. Sorry, the thin surface crust, but there's semi-molten aspect that can create the plate tectonics. So a planet that is too small, such as Mars, would cool too quickly so that the plate tectonics could never start. It appears that there's a minimum size somewhere between the size of Mars and the size of Earth planets to have this carbon-based life. So planets smaller than that minimum size might not be able to sustain a carbon cycle. So astronomers think that carbon-based life is the common life that we should be able to find in the universe. So that's why we are searching for exoplanets that's the same size as the Earth, or little bigger than Mars, but not bigger than Earth. So Earth-like planets. So we are searching for Earth-like planets in the universe. Well, so if we put this into a picture about the carbon cycle, so we have trees that produces carbon dioxide as in the breathing process. So carbon dioxide get emitted into the atmosphere from trees, and also animals will eat trees, or animals feeding from the trees. And then in the respiration process, the animals are emitting carbon dioxide into the atmosphere. Then the plants or the animals get decomposed and get into fossils. Then from fossils, we will be getting fuels like oil, coals, and gas. Then from the extraction, we do combustion into motor vehicles or some other way. And then we are emitting carbon dioxide into the atmosphere back again. So that's called the pollution, because we are externally adding these carbon dioxide percentage into the atmosphere. Then there are two ways that the carbon dioxide can be removed from the atmosphere. One is the photosynthesis, where trees are using this carbon dioxide in the process of creating glucose. And then the other process is carbon dioxide get dissolved in the oceans by the water cycle, and then it gets into the sedimental rocks and create the limestones and shells. So calcium carbide compounds will be created by using this carbon dioxide in the atmosphere, which was dissolved in ocean. So this is the carbon cycle. So if we break this one somewhere, then we are destroying the compositions in the presence of carbon dioxide in the atmosphere, which will affect in the life, right? So this pollution is getting bigger and bigger. That means we are creating more carbon dioxide in the atmosphere. So the energy sources of life. So maybe you have heard in your school, in your middle school, if you have taken science classes, so energy is conserved. That means energy cannot be created or destroyed. However, it can stored and released, and also it can transferred from one place to another, and also it can change their form. So here, if you think about a slide, so when you're sitting all the way up, it does have, we have a high potential energy because we are above the ground. But when we are coming down, the potential energy will be converted into kinetic energy, and all the way down, it's getting, we will be getting speed up, right? So we are receiving kinetic energy at the end. And also when we are sliding down, we feel the heat. So we are using that energy, the potential energy, converted into frictional energies like heat, and also the kinetic energy. So the energy cannot be destroyed, but can be transformed into different formats of energy. So energy that comes from the sun. So for most of the life here on Earth, the basic energy input comes from the sun, right? So the chlorophylls that's in the trees will absorb this energy from sunlight and create the food. So the plants use a complex molecule-sized chemical factory consisting of several chlorophyll molecules to convert water into oxygen and hydrogen. So we call this as the photosynthesis. It's create oxygen and hydrogen. The hydrogen is generated as separated protons and electrons, which are then used in other processes to convert carbon dioxide into complex hydrocarbons. So the oxygen is released into the atmosphere. So in the photosynthesis process, the oxygen will be removed into the atmosphere where we are using it to breathe. So this is a chemical reaction formula for photosynthesis. So 6 carbon dioxide molecules will combine with 6 water molecules and create glucose and 6 oxygen, right? So here it's producing oxygen. So carbon dioxide and water mixed up and create glucose and oxygen. So this is the process of photosynthesis, but for this reaction to happen, we need energy. That energy is coming from the sun. So when we look at around, you will be seeing the most planets are in green color. So why do we see the plants in green color? And it is very comfortable into our eye. Like imagine like if we see all the trees are in red color, it will be really distracting to us, right? But luckily all the trees looks in green color and it is comfort our eye. So in this diagram, you can see the absorption percentages, and here this is the visible light electromagnetic spectrum wavelength. So at this end of the spectrum you can see the light that mostly violet and blue. Here at this end you see the red color light. So absorption spectra, if you track this one here, 100% absorbed, right? So the purple color or the blue color get 100% absorbed, and also red color get absorbed as well. So let's look at it, this graph little step by step. So the largest number of photons that reach the Earth's surface are photons of red light. So chlorophyll absorbs those and uses their energy. So chlorophylls are absorbing red color a lot. And then the highest energy photons that reach the Earth's surface are photons of blue or violet light. So chlorophylls uses those after steeping their energy down to match its needs. So it is too much, but chlorophyll can use the correct amount. So it's crashing this energy into pieces, and it can absorb 100% of this light. Then the middle of the visible spectrum, where you see this from light blue to yellowish color. So this middle part of the visible spectrum has photons that are not the most abundant and are also not the most energetic. So chlorophyll does not use those. So you know, like chlorophyll does not like to do much work. So it's using that energy that available in the spectrum. So red light and the blue light or the violet will get absorbed a lot into the plant from chlorophyll. So as a result, we have plants that absorb energy from either end of the visible spectrum and reflect the green light that is in the middle. So blue light and the red light get absorbed, but the remaining green color will be visible to our eye. Then we can receive energy as a form of hot water. So one alternative energy source, the heat from the interior of the Earth. So the same thing that drives plate tectonics. So at sea vents called black smokers in the floors of both the Atlantic and Pacific Oceans, water heated to 400 degrees Celsius, just upward into the ocean. So this is a picture of that smokers. So very hot water get shooted into the ocean. So the water does not boil because these vents are typically 2,100 meters below the sea level, and the pressure keeps the superheated water in liquid form. right? Because it's 400 degrees Celsius. So we feel like water should be boiling because it's water boils at 100 degrees Celsius in the ocean level, right? So here it is not, because it's all the way down to 1,100 meters below the sea level. So the pressure is really high. That's keep the liquid form of water. The water contains dissolved metal sulfides that precipitated out when they heat cold seawater, forming black channels. So each year, about 370 trillion gallons of water passes through these smokers, carrying that heat from the ocean beds. Chemical energy. So this picture, what is this picture? It looks like some animal, right? So let's see what it is. So the bacteria, it's a picture of bacteria in enlarged picture. So these bacteria use a process called chemosynthesis to convert methane and carbon dioxide into organic matter by using the oxidation of hydrogen or hydrogen sulfide or ammonia as a source of chemical energy instead of using sunlight. So these bacteria are live in the all the way deep sea. So the sunlight energy will not reach to them, but they don't need sunlight to create this energy. So the bacteria then supports more complex organisms such as this tube worm, worms that is filled with symbiotic bacteria. So these can grow to as much as 8 feet long. So this picture, so the picture that you saw earlier, it's a picture of tube worms, and it's filled with bacteria that does not use sunlight. However, it can create energies using other chemical sources. So photosynthesis in the dark. So photosynthesis does not have to use sunlight at a depth of 2,500 meters off the coast of Mexico. There are green sulfur bacteria that uses the faint glow, mostly invisible infrared light from a black smoker to power their activities. So even though astronomers are believing on carbon-based life with the presence of sunlight and creating photosynthesis process and all, there are some places that we don't need the sunlight to create the photosynthesis. So photosynthesis can happen even in the dark. So searching for life in the universe is not an easy task because we are looking at the things in our limitations. So maybe the limitations are not limited by many things, right? So searching for life is not an easy task. If you're interested, you may join to a group of scientists and start searching for the life in the universe. All right, so thank you, and please answer the questions, and I'll see you in the next class.